Alright, so you need to remember that energy equals Planck's constant times frequency, which is the equals Planck's constant times the speed of light over wavelength. Okay? A lot of mumbo jumbo. All you really need to know is energy is related to frequency by some constant, which is related to 1 over wavelength. That's what you really need to know, okay, for this class. Energy equals frequency, which equals 1 over wavelength. So if my energy increases, what happens to my wavelength? Decreases, right? Alright, next thing you need to know with this energy stuff. I give you a graph like this. Is this continuous or a line spectrum? Continuous, right? You see it emitting something over all colors. I tell you that my specific compound is a line spectrum, and it emits right here. So this is compound A. Okay, so this would be a line spectrum, right? I just have one line at certain spots. If I see compound A mainly emits at 750 nanometers, what color is it? What color does it emit? Red, right? This is blue. If I know that I emit at a high wavelength, do I have high or low energy? Do I have high or low frequency? Low. Good. Last thing, I know there's a lot of last things, but next thing, remember when you go up in energy level, so when I excite electrons, okay, so this is my ground state, this is my excited state, okay, alright, so I excite an electron from the ground state to the excited state. This is because I plug the box in, or I plug whatever is emitting light in, okay? So I plug in. Okay. This is when it what? Absorbs or emits energy. This is absorbing, right? I see that after I excite it, I let the electron fall back down. This is when it emits a photon. Okay? This is emission. Make sure that you understand when I excite an electron and it goes up in energy level, that's absorption, takes in energy to shoot up to the next level. When it falls back down, that energy has to go somewhere, right? It has all that energy bundled up, it kicks out a photon. Okay? Does that make sense? Okay. Okay. Everyone good on exam 1 stuff? Color range? Yeah. Oh, so it's just Roy, G, Biv. Backwards. Yeah. And so if you don't remember, this is IR, this is infrared. Red is near infrared, and over here is UV. Okay. Are you guys ready for exam 2? Hybridization and all that fun stuff? This is like a chemistry workout. I'm sweating. Exam 2. All right. What I'll talk about first.
Are you doing this tomorrow also?
Tomorrow is a really small room. It's like only like 40 chairs. It's really ridiculous. So it's going to be more like whatever you guys want to talk about. Yeah. Tonight it's more formal. All right. Exam 2. What do I want to talk about? All right. I guess first thing I'm going to talk about is electronegativity and polarity. So electronegativity, En, and polarity. So for electronegativity, what's that weird word that I told you guys over and over again?
Bunko brush.
Bunko brush. Good. Remembering that between carbon and hydrogen, these guys are considered to have similar polarity. These guys are nonpolar. All these guys over here, when compared to the last one, are increasing in electronegativity. Okay, going that way. instance, you have to draw the best Lewis structure. That way you can see, for instance, what has the strongest electronegativity and how does it affect the pull on the electrons. All right. So for electronegativity and polarity, next thing I want to talk about is intermolecular forces. You guys remember several. Dipole-dipole, dipole-induced dipole, hydrogen bond, ion-dipole, ion-induced dipole, and dispersion. Yes, okay. Intermolecular forces. So remember, if I have a dipole, am I polar or nonpolar? Polar. If I, no dipole, nonpolar, okay? Again, you have to draw the best Lewis structure. I'll go over that in just a second when we talk about hybridization. Okay. So being able to recognize, if I give you two molecules, for instance, water and water, you would know that the intermolecular forces between those are dipole-dipole, hydrogen bond, and dispersion is always present. Yes?
I know that for exam 2, Deloitte didn't ask us for all those. She only asked us about 3 of them. Can we expect that?
Well, since they have me teach you all 6, I'll still teach all 6 just in case. Yeah. All right, is everyone good on understanding polarity and all that stuff? Because I want to focus most of this on getting you guys back up to speed on Lewis structures and hybridization. Everyone cool with this? Okay. Just memorizing if you can see if something's polar or nonpolar, and then being able to apply the correct intermolecular force. All right, so let's talk about Lewis structures. Structures. First things first, always put least electronegative in center. Okay. Second, connect atoms. Third, calculate total valence electrons. Okay. 4, subtract bonded electrons. I know I'm going fast, guys, but we don't got that much time. Subtract bonded electrons, 5. Put remaining around atoms. Okay. All right, and then 6, calculate formal charge. And then lastly, minimize formal charge. All right, so I'll give you compounds such as, start off O3. Okay. All right, so for this, is there anyone that's the least electronegative? No, right? So I'm just going to connect my atoms, go to step 2. Calculate my total valence electrons. I know that oxygen has how many valence electrons?
6.
Times 3 is 18. So 1, 2, 3, 4. So I used up 4. I got 14 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right. Subtract bonded electrons, put remaining around atoms. 6, calculate formal charge. Does everyone have an octet?
No.
No, obviously formal charge isn't minimized yet, right? So, maybe some of these guys can share electrons. Okay. Okay. All right. So, now I'll calculate my formal charge. Here it's -1. Here it's +1. Here it's 1, 2, 3, 4, 5, 6. Here it's 0. Adds up to 0. That's great. Something's weird. Also remember your formal charge. So step 7, I'll add total formal charge must add up to compounds charge. For instance, here I see that the total charge for O3 is 0, so I know that once I add all these formal charges up, it must equal 0. Is everyone in this room good on calculating formal charges? Okay. Everyone good in finding the best Lewis structure? As long as you follow these rules step by step, you should be able to get to the best Lewis structure. Yes?
What's the formula to calculate the formal charge?
Yeah, so formal charge equals your valence electrons minus, you can say box electrons, so I like to say box electrons, which means is if you put a box around each one of these atoms, I see that I have 1, 2, 3, 4, 5, 6, 7. Okay. Yeah, if the box way doesn't work for you, the same thing is just valence electrons minus half the bonded electrons minus the lone pair electrons. I just think it's easier to draw a box. What's that? Yeah, the quick way is just drawing the box around it, and I know. Yeah, what's the other one? I don't know.
I think it's just counting the line rather than counting 2 dots and just finishing just one. So it's kind of like saying half, basically.
So what?
So it's dots, no, valence lines minus dots.
Valence lines.
Yeah.
I don't know. Yeah, whatever works for you guys, that's totally fine. These are the 2 ways that I know how to do it. And if you find some way that works for you, that's great. And if you want to share, that's good too. Do you know the other way? Or?
It was something like what I was saying. I was like dots minus dots and like matches minus. I don't know. I can't figure that out.
Okay. Well, this works too. So if you just take the valence electrons minus whatever's in the box. Is everyone good on valence electrons now? Okay. Cool. All right. Next, let's go into hybridization. Hybridization. So first step for hybridization is draw best Lewis structure. Second step is calculate the, what's it called? I just forgot. Nope. Other word. What? No.
Oxidation states?
No. Guys, come on now. Electron domains. That's the word I was looking for. Alright, calculate electron domains. Step 3, remember that your number of electron domains equals your number of hybrid orbitals, which equals your number of sigma bonds. Yeah. Sigma bonds. Been a long time for me too, guys. Sigma bonds plus lone pair electrons. Okay? So anything that is a non-hybrid is what? Pi bond. Okay? So also remember that. Non-hybrids equal pi bonds. Okay, so let me give you an example. I give you the following molecule. CHClO. I have to draw the best Lewis structure. Again, we know that least electronegative goes in the center, so that's who? Least electronegative carbon, right guys? Yeah, sorry. Least electronegative is carbon. Then I just connect the atoms, okay? I got an oxygen, have a hydrogen, have a chlorine. Can chlorine ever go in the center? No, right? Halogens can't go in the center. Can hydrogen? No. Hydrogen and halogens cannot go in the center. All right, have to draw the best Lewis structure. You guys can check this at home. Once you draw it out, you see that this is the best Lewis structure. Now, the question that I ask you though is, what is the hybridization? All right, so in order to figure this out, I have to calculate the total number of electron domains. If I ask for what is the hybridization on carbon, so here, how many electron domains does carbon have? 3, right? Number of electron domains equals 3. Why? Because I have 3 locations in space where carbon's electrons are located. I have some right here, some right here, some right here. Add it all together, I have 3 electron domains. So if I have 3 electron domains, how many hybrid orbitals am I going to create? Okay, and how many sigma bonds or electron lone pairs should I have? Great, good. Okay, so the way I like to do this is set up the boxes. Okay. Over here, this is never going to change. This is just our valence electrons. Over here, this is our hybrid and non-hybrid. Okay. All right, so again, this is never going to change. This is just the valence electrons on carbon. So we know that's always going to be those outer s and p electrons, right? Whatever's on the top of the top, not including 1s2. I just found the electrons I have all semester. So carbon has 4, so I'm just going to go 1, 2, 3, 4. Okay. Next, I'm going to hybridize. This just means mix s and p. So I'm just going to mix my s and p electrons, okay? So how many hybrid boxes should I create? 3, right? I have 3 electron domains. I better create 3 hybrid boxes. How many boxes do I have left over? 1. Where does that go? Non-hybrids, right? These are my non-hybrids. These are my hybrids. Okay? All right, how do I fill my electrons in this box? Counterclockwise, starting at the bottom left. So I see I have 4, so I just go 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. Just keep going around in a circle. Okay. Okay, so it comes down to the question, what is the hybridization? I took 1s. I took 1s and 2 p's. Thus, the hybridization on carbon is sp2. Okay? And that is how you figure out the hybridization. Yes?
Our lab teacher basically would just draw the Lewis structure and then just count like how many bonds or something like that.
You can't. Let me see.
Just look at it and like look over it. So if there's like a 4th atom, it would be SP3.
Let me see if that works. Yeah, I guess that could work. I haven't tested it out with everything, but if you guys want to practice, so if you guys want to hear what that guy said, he said that what you could do is just count the number of bonds with it. So it's just start somewhere in the structure and just say sp2 or sp3, for instance. But I haven't tried that with every atom. So, for instance, like group 1, group 2 guys, and group 3. I don't know if that works yet. But if you guys want to try it at home and see if it works, you guys can totally use it on the exam. Good. I'm always into shortcuts, so. Any other questions on hybridization? Yeah. Right, here? sp3. Okay, lastly, bond order and bond length. If my bond order increases, what happens to my bond length? Decreases, right? Bond order, so for a triple bond, my bond order is 3, right? Yeah, for bond order, it's 3 for a triple bond. Double bond, it's 2. Single bond, it's 1. Yeah, sir?
Where did you get like the 4 arrows that are in your, is that the valence electrons for carbon?
Yeah, just the valence electrons, and you just plug them in the same way you've done all semester. Yeah. So yeah, for bond order versus bond length. So remember, as this increases, bond length decreases. So if I have, for instance, a carbon triple bond versus a carbon single bond, okay, who has the longer bond length? Single bond, right? Who has the higher bond order? The triple bond. Okay. All right, is everyone good for exam 2 stuff for the most part? Yeah. Questions back? Oh, okay. All right, again, guys, I'm just barely skimming the top here because we only got 3 hours to go over an entire semester's worth of material. Lastly, I want to talk about stoichiometry for the last 20 or so minutes.